Okay. So again, this is the challenge of calculus. Unlike algebra, which which very often is presented as like just go do these steps, go do these steps, go do these steps. Y'all are past that. You've graduated. Congratulations. Now things get hard. Now it's real. Like I'm really trying to fight to prove to y'all that math is a model of logic. There's a lot of logic that's going to go behind the stuff we put on the paper. So don't approach this from a rules or a, but it worked last time. None of that will serve you in this class. It's all got to make sense. Otherwise, it's worth nothing. All right. So if we are talking about limits, what do limits mean? That's a question for you, Catherine.
That it reaches a certain point, and then from there it stops.
Very close. It doesn't ever reach. It forever approaches. Okay. So this goes back to the example I was talking with Dan. This idea of 0.9 repeating. This right here is a story of approach, right?
Mm-hmm.
Literally, I can chunk this out where it's 9/10 plus 9/100 plus 9,000. I'm just increasing it over and over again, like again and again and again and again. It's getting closer and closer and closer and closer, right?
Mm-hmm.
Does it ever reach? Not necessarily on the left-hand side, or at least not so it appears. On the right-hand side, we say equals 1. How come? Because there's a lot of logic that we backed up to say, in truth, forever approach is the same thing as getting there. So we've got to start with that. Are we good with that?
Yeah.
Okay. So this notation up here of limit, this means forever approach, which we want to think of in the back of our mind as a list, as a sequence, in the same way as this right here would be a sequence of saying I was at 0.9, and then I was at 0.99, and then I was at 0.999, and I'm just making a list that is forever approaching what's at the end of forever? 1. Do you see how it's a little paradoxical in nature? What's at the end of forever? That makes no sense. But what am I forever approaching? 1. We feel all right with this?
Yeah.
Okay, so that's what's happening over here, is that this whole limit as x approaches infinity, we're imagining a forever long list of approach. Okay?
Okay.
All right. If we want to solve this problem, most people say, since x is getting forever big, which is what this says right here, we could just plug it in. That's what we've done for all of algebra, right?
Mm-hmm.
All right. Is that going to work here?
No.
Now, is that a no because you've heard it, or no because you understand it?
Well, because infinite, it's not like an actual number. You won't actually get like the solution.
How do you know?
Because it would cancel each other out, and it'll just equal to 1.
How do you know that equals to 1 is wrong?
That I'm not sure about.
That's okay. This is like, do you notice like this, by the end of the semester, you can ask Dan, because Dan had me last semester. By the end of the semester, you're going to have a little mini Kevin that sits on your shoulder and is just constantly going, why? Because if you can't explain it as true, then no one's going to believe you that it's true. Fair, Dan? Yeah. That's, I'm going to be real annoying with it. I'm going to be the accountability partner from hell. Like, I'm just going to be absolutely berating with the why, because doesn't get me the right answer. My teacher didn't tell me to, not how I've used it before. None of that works in my class. None of that is worth a dime, because it's all just, I'm trusting the person who's in front of me, and I don't like that logic anymore. I'm going to make it so you all can convince each other. All right. So this doesn't work because it makes no sense to do 5 times of forever. If forever is already the longest thing, then there's nothing past it. So we can't do any of the logic of infinity plus 1, infinity times 5, infinity divided by half. What's half of forever?
It's just forever.
Do you see, like, but it should be smaller, right? It should be half. So like what we're recognizing is that forever as a concept does not work with ideas of addition, subtraction, multiplication, any of algebra. So plugging it in is already just a whole bunch of guesswork, and it's guesswork that's often wrong. Okay? So instead what we do is we try a very creative strategy. We decide instead of trying to plug in infinity, we try to understand the behavior. Now, you tell me, if I was going to plug in bigger and bigger x values into everything in this equation, what would happen? Like, let's plug in 1,000. 1,000's pretty big. What would we get?
So it'd be like 5,000 to the fourth plus.
So 1,000 to a fourth. Big number, small number?
It's a big number.
Big number. And then we're about to add 1,000 squared. What's bigger, 1,000 to the fourth or 1,000 squared?
1,004.
How much bigger? A lot bigger, a little bigger?
A lot bigger.
A lot bigger. And we're only at 1,000 right now. If we plugged in 1,000,000 instead, would x to the fourth be a little bigger or a lot bigger than x squared?
It would still be a lot bigger.
A lot. In fact, it'd be more bigger, right?
Mm-hmm.
So what we're recognizing from the story, from the behavior of this equation, is that this right here is driving the growth of the numerator. Do we feel good with that?
Yeah.
This is becoming more and more inconsequential. Do we agree with that?
Mm-hmm.
All right. On the denominator, what's driving the growth?
The 2 x to the fourth.
The 2 or the x to the fourth?
X to the fourth.
The x to the fourth. So what I've got right now is, regardless of the numerator or the denominator, x to the fourth is the biggest thing, right?
Mm-hmm.
So what we're going to do is a strategy that scales this down. It scales everything down. So instead of it being in comparison to numbers, it'll be in comparison to the x to the fourth. I'm going to try to bring the x to the fourth down to a place where I can touch it, I can manipulate it, I can look at it, and I'm going to let everything else be in terms of it. So what we'll do in order to make that happen on our paper is we'll multiply the numerator and the denominator by 1 over x to the fourth. First of all, have I changed the meaning of the original problem, or is it still the exact same thing? Just looks different.
Still the same.
Same thing. I can multiply the top and the bottom by any number, so long as it's the same number and that number is not 0, right?
Mm-hmm.
All right. And since we're talking about big positive x values, no worry about it being a divide by 0 error. Got it. All right. Simplify this one up for me. What do we get?
1 to the 5x to the 8th plus 1.
Hold on. 5x to the 8th? No, this one's on the denominator. This is multiplication on the numerator. If we multiplied it on through, wouldn't that be 5x to the fourth over x to the fourth?
Oh, yeah.
Okay, cool. What's the next one?
X squared over x4.
X squared over x to the fourth?
Yeah.
What about in the denominator?
2x fourth over x to the fourth.
2x to the fourth over x to the fourth. I'm going to write it different, but it doesn't matter. All right.
And then minus x to the third over x to the fourth.
All right, cool.
And then minus 4 over x to the fourth.
All right, excellent. Can we simplify that up and make it look a little nicer?
Well, yeah, the 5 and the 2, I'm guessing.
So what do we get on the numerator?
Wouldn't it just be like 5 over
5?
2? Over 2?
Why over 2?
Because of the 2 on the denominator.
2 on the denominator. I'm just talking about the numerator. Help me out with the numerator first.
Oh. Yeah, it would just be 5 and then plus x squared over x to the 4th.
Simplify this up. How can we simplify that? X squared is x times x, right?
So it would be x over x squared.
So x to the 4th is x times x times x times x, right?
Mm-hmm.
We can simplify some of these, cross them away, right? Tell me if I'm losing you, or tell me if you feel good.
Oh, so it would just be x over x squared.
So instead of guessing, let's see if we can figure it out. The same thing divided by itself. What is that?
1.
1. So after I simplify all these out, I've got 1, and I still have some division happening, right?
Yeah, x squared.
1 over x squared. Very good. And this works because x is not equal to 0. There's no divide by 0 errors. We can make a little note of that. Okay, good. So over here back, I've got 1 over x squared. We feel good.
Mm-hmm.
Okay, good. That's the numerator. What about the denominator?
Wouldn't it just be 2?
2. What about the next thing?
And then wouldn't that just be the same, like minus x squared over x?
So how about instead of wouldn't that just be, you say it is because. It is this because, and then tell me the because.
Because 3 and 4 are not evenly divisible.
Good. So after they cancel away, how many will I have left and where?
Just 1 or the denominator?
1 on the denominator, right?
Mm-hmm.
Good. See, when it comes from the because, you're feeling good with that. What about the last one?
And it would be 4.
Anything to cancel away there? Any simplification?
Well, no, because 4 is just 4 itself, and then
Very nice. See, when you get the because, that's excellent. The tone of your voice changes. It's really good to hear. That's exactly what I want from you. Good. All right. Now that we have this, remember, we're playing with a list of forever approach. We're considering as x gets bigger and bigger and bigger and bigger, we're imagining a list. We're imagining how that list trends, right? All right, so let's take a look. As x gets really, really big, and I make my list, which is what this says, make a list as x gets really, really big. 5 is going to change or stay as 5?
stay.
Right, 5 doesn't change. There's nothing affecting it. That'll be 5. I like it. What about this? What's 1 divided by bigger and bigger squared numbers? That's hard. Maybe we should try some things. Like, let's try x equals 10. So what's 1 divided by 10 squared?
And it'd just be 10 squared?
1 divided by 10 squared. 10 squared is?
Or 100?
100. 1 divided by 100 would be?
100.
1 divided by 100 would be? You can try it with your calculator if you want, or you can try it with a story problem. If I wanted to split up 1 cookie amongst 100 people, everybody does not get 10 cookies or 100 cookies.
I mean, 1 over 100.
Good, which we could maybe write that as like 0.01 if we wanted as a decimal, right? Or as a fraction 100th. I like that. Good. All right, what if x is 100? What's 1 divided by 100 squared? Take your time, use your calculator or resources that you want. Make sure you're locking in an answer that you understand. What's 1 divided by 100 squared?
1 over 10,000.
1 over 10,000, or a 10,000th, which would be 3 decimals, I think, of 0 and then a 1, right?
Mm-hmm.
Okay, so we start to get the idea. As x gets bigger and bigger, we're only on 100. We haven't even got to 1,000, 10,000, million, billion, trillion. Haven't even got close to there. And I'm already getting really small numbers. You tell me, if I start making this bigger and bigger and bigger and bigger, what is this getting closer and closer and closer and forever close to?
They're getting smaller.
They're getting smaller. So what are they getting smaller? Are they going to get forever small? If we keep plugging in bigger and bigger values, will they get forever small?
Yeah.
Okay, so then what is at the end of that forever? What are they getting closer and closer to?
So they would get to like negative.
Are these getting negative?
No.
No, then they won't ever touch the negative. So now we're on the smallest positive number. Okay, so we're going to stay positive. What's the smallest size?
0.
0. Do you agree with that? Like from your core, would you agree that 0 is the smallest size?
Yeah.
And these numbers are getting forever small, right?
Yeah.
So if they get forever small, they are approaching 0. Is that what I'm hearing?
Yep.
And that feels good from Catherine logic, right?
Mm-hmm.
That's exactly right. So we're playing with make a list as x gets really, really big. This story problem says I'm dividing by that really big number. In fact, I'm dividing by that big number after I've made it even bigger. So it's saying if I did that and I do 1 divided by big number, divided by bigger number, divided by bigger number, divided by bigger number, what am I getting close to, right?
Mm-hmm.
So let's try that on the bottom now. So we've got 2. As x gets really big, does 2 change?
No.
No. Is that a question or an answer?
As x gets big.
If I say x is equal to 48 billion, how big is 2? How big is 2?
Well, 2 is still going to be 2.
There you go. I want that to come from you, right? There, that's true. 2 is always 2. Excellent. What about this thing? 1 over x. As x gets really big, which is the list I'm considering, as x gets big, what's going to happen to 1 over x?
It's going to get smaller and smaller.
And you feel good with that, right?
Yeah.
So at the end of it getting forever small, what's it approaching?
0.
Very good. All right, what about the last one? Minus 4 over x to the 4th. As x gets really, really big, 4 divided by bigger and bigger and bigger and bigger?
It'll get smaller.
Smaller?
Yeah.
So what's at the end of that forever?
0.
There, the answer, you're asking it like a question. Is it or no? Give me the because.
I think it's 0 because
Not I think it is. It is because.
0 is the smallest positive number.
I love that. Good. So that means that now after I've considered the list and after I've used my logic, and this is the hidden part, this is the difficult part about limits. All of this happens behind the scenes. This all has to happen behind the scenes for each individual piece. So it's hidden from our work, but it has all of that story that we've developed so far. Now that we've kind of considered, okay, I've got a forever approach. My forever approach is going to land me closer and closer to a thing that it eventually is at the end of that forever, whatever that means. So we get all of this as a settling point. This is the settling point it's getting closer and closer to. How do we simplify that out?
It would be 5 over 2.
Be 5 over 2. Now we can go back and double check a few different things. Does it make sense now that we go back to our original problem? Because remember, you told me that this looked like it was driving the change of the numerator, right?
Mm-hmm.
And this was driving the change of the denominator, right?
Yeah.
And as it gets bigger and bigger and bigger, these are going to be the things that matter most of all, right?
Mm-hmm.
And they're changing in relation to each other. So it makes sense that as we go super, super big, the 2 leading highest degree powers are going to be the most important things, and they're going to balance each other out to be about 5 times bigger on the top than the 2 on the bottom, right?
Mm-hmm.
And there we are. Now compare that against what happened when we tried to plug in infinity. That didn't make any sense because we couldn't do any of the operations and it disguised those details.
Mm-hmm.
So that's the idea. Whenever we're playing with limits, we are imagining a forever long list. We've already run through the logic in the class that says a forever long list that approaches can be replaced with the settling point that is supposedly at the end of forever. So now we're starting to make that appear in our work. How do you feel?
Better.
It's a lot, but I want it to feel like you understand it and not just we can do it. Are you on board with that part?
Yeah.
Okay, excellent.